So AP Stats, we have now made it to Unit 2, and that starts with Chapter 7. So the way that we are going to break down Unit 2 is as follows. We are going to group Chapter 7 and Chapter 8 in terms of test, and then we are going to conclude Unit 2 with Chapter 9 and Chapter 10. And then we will test on the entire unit afterwards. So test 1 and then test 2. If we want a little bit of a breakdown of what each of these chapters are as we move into Unit 2 and we're comparing multiple variables that are quantitative, most likely. So Chapter 7 is our big overview chapter of what does it mean to look at scatter plots and identify association and talk about its correlation. Chapter 8 is the details. How do we do these calculations, and how can we go from problem to problem, and what are the specifics that we need to understand? Chapter 9 focuses on outliers and gaps and things that have leverage in a linear regression. And then Chapter 10 is more about what happens when we are not so linear. So similarly, think of it like Chapter 4 when we were talking about, okay, here are quantitative variables, and then what are the big ideas there? We talked about shape, outlier, center, and spread. With comparing variables and looking at two quantitative variables, we want to also look at similar ideas in this tape. Instead of looking at this idea of socks like we had before, we're going to talk about sods. I know it will sound familiar. That's why I'm trying to group these two together. So this chapter, focusing on just Chapter 7, will be broken down into two videos. We're going to watch 7.1 and then 7.2. Then we're going to complete the homework problems. We will have a Chapter 7 quiz and a Chapter 7 free response question. And that's how we're going to do in this order. So I highly suggest you watch these two videos first, and then we go homework, quiz, free response question in that order. So here are our objectives. With Chapter 7, we are going to be focusing primarily on calculating Pearson's product moment correlation coefficient, or what most of you are just going to refer to as Pearson's R, or the R value. And the R value comes with linear regressions, or a linear model. And when I say linear, I mean we're making lines. This is what I mean by it should be familiar to you guys because we've covered lines a lot in all of your previous math classes. So in order to get to our linear modeling that we are going to spend a bunch of time in this statistics course, let's first talk about scatter plots. So with a scatter plot, and scatter plots are often effective displays for data comprised of two variables, and that's what we're really focusing on. Can we compare these two variables? So in a scatter plot, you can see patterns, you can see the relationships between variables, and even find unusual values sitting apart from the overall pattern. We know this, we've seen plenty of scatter plots before. Scatter plots are used to begin to understand any relationship between variables, providing a way to picture possible associations, that's the first time we're seeing that, between quantitative variables. Note that we're saying quantitative variables. This is not for categorical, which is why we make that emphasis at the beginning of the year. Do you know whether it is quantitative or categorical variable? And then lastly, scatter plots are especially useful when there is a large number of data points because they provide information about the relationship between the two variables. We can start to see the pattern, which is why when we are dealing with scatter plots, it is always important that we draw a picture and visualize or use some sort of technology to visualize this data. With scatter plots, as always, we start our conversation with what the picture looks like. So we describe a scatter plot's characteristics as the strength, the shape, the direction, and presence of outliers. So shape, outliers, direction, and spread gives us SODs. And note, when we were talking about any quantitative variable, we talked about shape, outliers, center, and spread. So I'm trying to use these closely tied acronyms together to help us remember these things. Do note, whenever you're describing the scatter plot, you must include the description of these 4 characteristics. This is a non-negotiable. You have to do this in order to fully describe what's going on here. So when looking at scatter plots, we will look for the direction, the form, which is we're hoping for a line. That's what we mean by shape. The strength of our relationship, so how well does our data look like a line, and any unusual features. So this is where we would notice outliers or points of leverage. Both mean a thing, and we will talk about those in detail. When asked to describe a relationship between variables, we will describe, again, the direction, the shape, the strength, and any unusual features. Are you getting the point yet? In order to describe a scatter plot, we need to see these 4 things. Okay, so let's talk about what we mean by that. If we're talking about the direction is a pattern in the distribution that runs from the upper left to the lower right, which would give us a negative slope, is said to have a negative direction. So left to right, if our scatter plot is going down, we say that it has a negative direction. Similarly, a trend in a scatter plot running from the lower left to the upper right, think positive slope, is in a positive direction. What is important is that the behavior of one variable is in some way associated with the behavior of the second variable. So we're looking for this relationship, and we're seeing if one is associated with the other. Next comes shape. So shape or form. So to determine the shape of a distribution of a scatter plot is to determine what shape the curve best describes the scatter. So obviously, if it's a line or a straight line, we call that linear, which makes sense. If it's not a line, we call that curvilinear. We will spend plenty of time in Chapter 10 linearizing or making a curve into a line so that we can do this type of analysis. So think, is it a line or is it curvilinear? So note, there are other models that fit data, and the TI-84 and the TI-Inspire can calculate those models, but we will restrict ourselves in this AP Statistics course to linear models. These models are heavily discussed in upper level statistics. So if you want to spend that time with it, you can. It's there, but it's just not the focus of our class. So we've talked about the direction. We've talked about the shape. Direction is either positive or negative. Our shape is linear or curvilinear. How about the strength? What do we mean by the strength of our association? So notice that line we discussed in the previous slide is critical determining the strength of the relationship between 2 variables. The closer your scatter comes to actually being on the line describing the shape, the stronger the relationship. Whether it be a negative direction or a positive direction, the more concentrated or closely our scatter plot fits a line, the stronger the relationship. Likewise, the more scattered, the less our line fits our data, either low negative correlation or a low positive correlation. And if we have truly just a regular scatter plot and there's no discernible pattern that we can identify, we would say that there is no correlation. And no correlation will definitely mean a thing. So this is what we're looking for. Are the data points concentrated, and does a line describe those, or are they really spread out? So just to put this all together, to kind of do a redux, a scatter plot gives you an indication of the strength, or how close the points come to a line. The shape, is that a line, a straight line, or is it a curve? The direction, is the relationship a positive slope, or does it have a negative slope? And lastly, are there outliers? Are there any points off to themselves? Anytime you have a scatter plot, you must describe those 4 attributes. So think shape, outliers, direction, strength. Is it a line? Are there any outliers? What's the direction of the line? How strong is that line? Focus on those 4 things every single time you have a scatter plot. So let's try this. If we're looking at a driver's age to how well they see, what do we notice here? Well, in our scatter plot, let's talk about the shape. Does a line fit our data? Yeah, and we can see as we go left to right, a line, or if you wanted to, we could also draw in an oval or an ellipse to see how well our data fits inside there. Also note the numbers, the dots that we have here, fit well at younger ages, the lowest age being, 14 years and 9 months. And then there's a lot more scatter as we age, or there's a lot more variability in our data set as people get older. So we would say this is linear. It is a negative direction because our line is going down. It's probably a moderate fit in terms of the strength. Like it fits the line kind of, but the further we go out, there's more scatter. So we have a moderate, negative, linear direction between the age and sign legibility distance. Notice I identified my 2 variables in this sentence that we stated. Additionally, as age increases, the variability, the scatter that we saw in legibility distance has increased. So there's more scatter the older they are. It's worthwhile pointing out those interesting features. Okay, let's try another one. What is the relationship between per capita GDP and life expectancy? So we have 3 different times in this. GDP is how much a country makes in a given year. We're looking at 1952 versus 1982 versus 2007. Now there's a lot of information going on in this chart, but in general, if we are trying to fit a line of best fit, we see that this data is linear, it's positive, it's probably moderate to weak in strength just because there's a lot more scatter. The data points don't all fit there. We do have an outlier in 1952 of our country that has a life expectancy of around 50, and they made 100,000 per capita. So let's see how we did. The figure shows a weak, positive, linear direction between the GDP, variable 1, and the life expectancy, variable 2. There is a significantly less variability in the upper values of GDP. So what does that mean? If we are doing this analysis, as we go further to the right, more of our data starts to be concentrated together. That's what we mean by variability. There's less of it. Everything's closer, as compared to the big spread of our data at the lower ends. So the lower GDP, there's a lot more variability in terms of life expectancy, where some are living till 30 and other countries are living till 50 or 60. Now, when we're talking about form, if there is a straight line or a linear relationship, it will appear as a cloud of points stretched out in a generally consistent straight pattern. How closely do the points approach forming a line? Well, holistically, how close are the points to being on that line? And that's why if we use this idea of drawing in on an ellipse, how well does our line fall, or how much does our scatter plot fall onto our line of best fit? And in general, the narrower the ellipse, the greater the tendency to linearity, or the tighter the ellipse is, the more likely it's going to be linear. Also, the stronger the relationship, and thus the greater value of R. We'll talk about that in a second. So it is the tendency to linearity that we want to quantify. And that's where this idea of the correlation coefficient comes in. Now note, if we're looking at form, if the relationship isn't straight, but curves gently, while still increasing or decreasing, a linear model would not be appropriate. So in this case, we see that this is starting to slow down, And if we were trying to fit a line on here, it wouldn't do a good job of describing our data values, or a linear association, depending on how we drew that line, wouldn't be appropriate. So we may be able to, and often will, find ways to make this relationship more nearly linear. And by linearizing this curve, or if we take this exponential function and we maybe take the log of one of the variables, now this will become a line. Okay, put a pin in that, because that is what chapter 10 is about. So we're going to have to wait a little bit into the class until we take a curvilinear function and make it linear. But that doesn't mean we can't do it. Likewise, if you see something that looks quadratic or cubic or sinusoidal, there ain't no fixing this. We are not going to linearize this data set. So by looking at this, obviously you see that it looks like a curve or a quadratic. With this strong relationship, there's definitely a relationship here, but that's not a line. So we can find a strong quadratic regression, but that is beyond the scope of this course. Again, we are focusing on linear regression models, or lines of best fit. We're not going to fix something like this, but we can fix something that is curvilinear, if just a subtle adjustment would work. And then lastly, like in terms of this form, is it linear or not? If the relationship curves sharply, so here, then the methods of this course cannot provide a single model. If you're thinking solely in terms of lines, we would have to have 3 different lines to fit this data set, and that's just not appropriate. Again, it is possible to fit 3 distinct linear models to this data, but this is assuredly not a single linear relationship, and that's what we want to be able to do, because once we build a linear model, we can then predict values. So in terms of this, is it linear, is it not? Well, this goes also to strength. At one extreme of the strength of a relationship, the points appear to follow a single line. Again, whether it's straight, curved, or bending all over the place, we can still talk about the strength of a relationship. It's just, is it linear or not? So, for instance, our first relationship is a strong and linear association. Our second, our curve, is a strong quadratic relationship. It's just not linear, as we can see. And then our third, which is like a sinusoidal, it's a wave function, maybe it's a polynomial, could be either. It's strong relationship. There's a model that definitely fits that, but it ain't linear. And because our focus is only about lines, we are going to have to adjust those if possible, or just say that it is not a curvilinear relationship. So with strength, at the other extreme, the points appear as a vague cloud with no discernible trend. So overall, if there's no trend here, then no matter what line you have here, that line or that line or that line, the relationship is not going to be strong. And so what you might have to do is then go, okay, the general trend is not very strong, but what happens if you looked, let's just pick the color that's close to it. What happened if we looked at the blue lines? Or maybe we look at the data set as just females, the pink lines. And we focus on those subsets of data, we might be able to identify the relationships between those scatter plots. And note, at the end of this, the second video here, because we're already way ahead of schedule, we will quantify the amount of scatter soon. We're just not there yet. And so the last thing, if we talked about shape, strength, direction, what about these unusual features? So what do we mean by outliers here? Look for unexpected things, or the odd man out. What's far away from our scatter plot? Sometimes the unexpected values indicate something interesting in the data that was unanticipated. Perhaps this might suggest something that we have to follow up on, especially if you're creating your own research project. An outlier standing away from the overall pattern of the scatter plot may suggest something interesting or lead you in a direction you had not thought to investigate. Like maybe those are interesting data points that we should focus on. Likewise, clusters or subgroups within the data should also raise questions. Why is some of your data really concentrated on one location? Maybe we'll want to investigate that. That's what statisticians do. And then lastly, our roles of variables. It is important to determine which of the two quantitative variables goes on the horizontal axis and which one goes on the vertical axis. This determination is made based on the roles played by the variables. As you know, which one is the independent variable? Which one is the dependent variable? We've talked about that in many math classes previously. Sometimes the roles are not so obvious, and the variables can play either role. Sometimes the roles make more sense in one direction. Sometimes the roles are determined by what the researcher is attempting to explain. Regardless, the variable that you choose to be on the x-axis we call the explanatory or the predictor variable. That is what this independent variable is. The response variable, or our dependent variable, goes on our vertical axis, or our y-axis. The roles of the explanatory or response variable that you select for the variables may be arbitrary and could be more about how you perceive the relationship rather than the variables themselves. So does it make more sense to think about hours predicting score or score predicting hours? You can see that if you spend time studying, then you can also look at your test score. But you could also think about, well, what happens if we think scores and then try to see if scores are independent, and the hours study are then dependent? We could reverse those. And so sometimes it seems arbitrary, and it's worthwhile to point out what you're trying to find in your study. Though we call a variable the predictor, or the explanatory variable, placing that variable on the x-axis does not necessarily mean that it explains or predicts anything. Those are just the terms we use in order to talk about like things. The variable on the y-axis may not respond to it anyway. So in other words, there may be no association, or the association that is the result of another variable. Like there could be other things going on. So you're going to hear this phrase often, and I want it to stick in your head. Correlation does not equal causation. Just because there is an association between these variables does not mean one causes the other. And so what we mean by correlation here. Correlation is any measure of strength of linearity. Should be independent of the units of measurement used for the variables. So if you weigh yourself in pounds and you measure your height in inches, the relationship between height and weight should not change if you measure your height in meters and weight in kilograms. Now think, if we are trying to detach our variables from units, we should be thinking z-scores. The correlation coefficient is independent of the units of measure. So if the units of measure don't matter, let's remove them by calculating the z-scores, which we know have no units. So we're going to pause the video here. We have more than enough to start getting into this idea of correlation and the correlation coefficient. Part 2, or the last 20 slides, give or take, will go in depth on this concept of correlation coefficient and what are some common mistakes we make. I'll see you in the next one, Falcons.